Alright, today we're talking about free body diagrams. Remember, if you're struggling with this, the force is with you. Unless you're a Spaceballs fan, then the Schwartz is with you. Alright, today you'll be drawing and interpreting free body force diagrams. From henceforth, I will just refer to these, oops, backwards. I will refer to these as FBDs. A free body diagram. It's free, doesn't cost a thing. So just a quick review of Newton's first law: an object in motion stays in motion in a straight line unless acted upon by an unbalanced outside force. A push or a pull will cause an object to speed up, slow down, or change directions. Also some review. Forces are balanced. You got a force going this way. So object at rest, the velocity equals 0 meters per second. If they're balanced forces, that means the acceleration equals 0. I don't think I showed that. I'll show that real quick. So force equals ma. Net force equals ma. And if the net force is 0, everything's balanced. Obviously mass can't be 0, so that means acceleration must be 0. So acceleration equals 0. If an object's at rest and there's no acceleration, it will stay at rest. Similarly, objects in motion, meaning their velocity is not 0, if the net force equals 0, that means acceleration must be 0. And they will stay in motion, the same speed and direction. Direction is important because we're going to be talking about rotational motion real soon. There's always an acceleration if something's turning. So basically, objects just keep on doing. They keep on trucking. So they keep on doing whatever they're doing unless they are acted upon by an unbalanced force. So some Grateful Dead, just keep on trucking. So when we draw free body diagrams, they are used to show the relative magnitude and direction of all forces acting on an object. You're going to have a normal force pointing up, and this normal force is the force caused by an object just resting on a table. So if like this is a book or a box or a person and it's sitting on a table, force of gravity, their weight is pulling it down. And if it's not falling through the table, which would be kind of weird if it did, that means there must be another force acting the opposite direction to balance this guy out. The force of gravity, sometimes I might just call weight. So you just see me write W. These are the same thing. Normal force, often I'll just write it as F sub big N. Applied force could be pulling this way, and if this object is in equilibrium and it's sitting on a table, it's going to have some other kind of force acting against the applied force. Now we're going to be dealing a lot with friction, which occurs between two objects as they slide across each other. So normally our applied force goes one direction and our frictional force goes another direction. It could also be something like air resistance, like anything that opposes motion. Actually, air resistance is a type of friction. So basically, pretty much any force we talk about that opposes the motion of the object is going to be a frictional force. So this diagram shows 4 forces acting upon an object. There aren't always 4 forces. For example, there could be only 1 or 2 or 3 forces. So I mentioned the normal force before. So the normal force is a force that acts perpendicular to the surface of an object it is in contact with. So if I have a box sitting on a table like this, normal force is perpendicular to the table. If I have a box sitting on an inclined plane like this, first of all, this one's weight is going to be down. Weight, normal force. This guy, his weight still goes straight down, and this doesn't look straight down, it is. And normal force is perpendicular to the surface it's acting on. It's perpendicular to the ramp. Now this is where a lot of students mess up. They just assume that the normal force is just the opposite direction of the weight. It's not so. The normal force here does not pull straight up. And here's an example that might help clarify that a little bit. If I'm pushing a box against the ceiling, I'm going to have the force that I'm pushing it with, the applied force, going up. I'm going to have the weight of it acting straight down. And since it's touching the surface on this side, The normal force is going to be in the same direction as the weight. Normal force. Get it? Got it? Good. Let me erase that. So for example, you're sitting in your chair and your weight acts downwards. The force that the chair pushes back on you with is perpendicular to the chair. This is the normal force. So problem number 1, a book is at rest on a tabletop. Draw the forces acting on it. So in this diagram, there are normal and gravitational forces acting on the book. So here's the table down here. This normal force is perpendicular to the table. Gravity is going down, normal force is going up. And because this book isn't moving, you want to make sure you draw like the normal force line and the gravity force line roughly the same size. Doesn't have to be perfect. You don't need to get your rulers out. So problem number 2, an egg is free falling from a nest in a tree. We can neglect air resistance in this problem. Draw a free body diagram showing the forces involved. This one's easy. Gravity is the only force acting on the egg as it falls. Just gravity. This egg is just going to come straight down. Now if I would have said we can include air resistance is a type of friction. That means it opposes motion. Say the force of the air would be up. And when I draw it, we know this is going to fall. These can't be balanced, because if it was balanced, we'd just have eggs floating around everywhere, which would be kind of cool, unless you're allergic to eggs. But we know that doesn't happen, so the air resistance is smaller than the gravity force. So problem number 3, a flying squirrel is gliding. No, which means it's not flapping its wings, so it's not having an upward applied force. So it's gliding from tree to the ground at a constant velocity. This time we are going to include air resistance. A free body diagram for this situation looks like this. We have gravity pulling down and the air resistance pushing up. Now I drew these, this one should be shorter than this guy, but I didn't draw it that way, but it should be. I can draw it that way real quick. Get rid of like this stuff right here. Alright. A little smaller arrow, because they're not going to be equal to each other. Problem 4, a rightward force is applied to a book in order to move it across a desk. Consider frictional forces this time. We're going to neglect air resistance though. Construct a free body diagram, and let's see what this one looks like. So note the applied force arrow is pointing to the right, and notice how the frictional force points in the opposite direction. And finally, since it's on a table, it's going to have its weight, it's going to have a normal force pushing back. These guys are going to be equal though. If these guys weren't equal, the book would be going down or up. But the applied force, you can notice, is bigger than the frictional force, so we know it's moving this way. So whatever direction your net force is moving in generally is, well, whichever direction your net force is pointing in is generally the direction it's moving in. Unless it's like the object is slowing down. We'll talk about that too. A skydiver is descending with a constant velocity. We're going to consider air resistance. Draw a free body diagram for this. So gravity pulls down the skydiver while air resistance pushes up as she falls. So the air resistance and the gravity, the weight, are equal to each other in this case. They weren't equal to each other all the time though, because the faster you go, the more air resistance there is. And we're not going to worry about like the equations for that because they're absolutely ridiculous. Like I didn't even use them until my senior year in college in physics. But just know the faster you go, the more resistance there is. So I'm sure you've probably heard the term terminal velocity before. Like this is what happens at terminal velocity. The air resistance equals the gravity force. You're still moving down, you're just not moving down any faster. So you're not changing your velocity, so you've reached your terminal velocity or ending velocity. Problem 6, a man drags a sled across loosely packed snow with a rightward acceleration. Draw the free body diagram. It's going to look exactly like the book one does. We're applying the force this way. There's going to be some friction pulling it back that way. The applied force is going to be bigger than the frictional force because it's accelerating to the right. Normal force, gravity, they're equal, but in opposite directions. Football moving upwards towards its peak after having been booted by a punter. We're going to neglect air resistance. And for this guy, it's just like the egg. The football is just traveling upwards. Gravity is the only force acting on it, pushing it down. Problem number 8. A car runs out of gas and is coasting down a hill. So even though the car is coasting down the hill, there is still the dragging friction on the road, which is the left pointed arrow, as well as gravity and normal forces. So if we were really want to be careful drawing this, so here's our hill, here's our car. Let's make it a convertible. Yeah. And it's a really ugly looking car. I'm usually pretty good at drawing cars. Looks more like an upside down umbrella with eyeballs or something. But anyway, the car will be moving down this way. It's going to be accelerating this way because it'll be picking up speed. But the forces you put on like this. Here's the frictional force. Here's the normal force, which is perpendicular to the surface. And the weight going straight down. Now it's the component of this guy's weight. Remember components? So we're going to use these guys again, which is why we learn vectors. It's the components of this guy's weight. He has an x and a y component to his weight. Doesn't really look like an x and a y here, but there it actually is. And we'll do a problem, I'll show you in class whenever you get to it, about stuff on a hill. But the components of the weight that acts along the hill is what's pulling this guy down. And he still has another component of weight acting like perpendicular to this guy too. Actually, let me draw that a little better. All right. Hill. Here's how I draw cars normally. Just a box. Friction, force of friction. Normal force. Weight. Now this guy, its components actually look like this. It has a component of weight acting along the hill, same direction, or same angle, but opposite direction of that. And it also has a component of weight that acts opposite the normal force. So it's going to have a component right here and a component right here. We're going to call this one the x and this one the y. Because in physics, we can choose our coordinate system however we want, and we can put the y being perpendicular to the surface and the x like that. We'll get to that when we do a problem with that. So now let's take a look at what happens when unbalanced forces do not become completely balanced or canceled out by other individual forces. An unbalanced force exists when the vertical and horizontal forces do not cancel each other out, or the left and right, just anytime they don't cancel out. So for example, notice the upward force of 1200 newtons is more than gravity. Okay. And the gravity force, the weight, is 800 newtons. So from now on, when I ask you for the weight, I want it in newtons. This is weight. So the net force, we add these two guys together. So the net force equals 400 newtons upwards. That means this guy is going to start to accelerate upwards. Always have to put an acceleration arrow when you're drawing your free body diagrams to show which direction it's accelerating in. Another example, notice that while the normal force and gravitational forces are balanced, each are 50 newtons in this case, the force of friction results in an unbalanced force on the horizontal axis, and the net force is 20 newtons to the left. So which way is this guy going to accelerate? This way. His velocity could be this way, to the right, but acceleration is this way. That would mean he would be slowing down, which is what friction usually does. It slows things down. And remember, acceleration and velocity, they're both vectors. If they point in opposite directions, the object is slowing down. So another way to look at this, two arrows go in the same direction, add them together, 10. Two arrows go in the opposite direction, add them together, equals 0. This guy, both in the same direction, 5 and 10, you get 15. This guy, 5 to the right, 10 to the left, you get -5. And so on, and so on, and so on. It works the same up and down as it does left and right. So which one of these, these little dots each represents the distance between them represents about 1 second each. So which one of these has a balanced force? Remember, balanced means our net force equals 0. And net force also equals mass times acceleration. Now mass isn't going to be 0, so that means acceleration must be 0. So therefore, A equals 0. So which one of these pictures shows A being equal to 0? It's obviously this car right here. The distance between all these points is the same. Distance between these guys is not the same. Not the same. These guys get closer together. These guys get further apart. We have a short distance here, and we have a bigger distance here. So obviously, if the distance is increasing, that means the velocity is increasing, which means acceleration isn't 0, because acceleration is a change in velocity. Balanced or unbalanced? Velocity versus time graphs. Velocity of this guy, constant, straight, doesn't change. That means A equals 0. That means net force equals 0. Balanced. Balanced. Velocity is decreasing here. That means acceleration is negative, which is not 0. Therefore, the net force isn't 0. Unbalanced. Again, velocity is changing. Change in velocity means there's acceleration. This acceleration is not 0. Net force, not 0. Unbalanced. Another couple quick little problems. Find the net force acting on these guys. Remember, you can only add x direction stuff with x direction stuff and y direction stuff with y direction stuff, just like we're doing vectors, because forces are vectors. So we add everything up and down. So the net force in the y direction for this guy is 0. Net force in the x also equals 0. So therefore, it's not moving up or down. It's just sitting still, or it's moving at a constant velocity. In this case, net force in the y equals 0, but the net force in the x equals 5, -5 newtons. That means it's accelerating this way. Acceleration. Draw those acceleration arrows. Acceleration is 0, right. Acceleration equals 0. This guy's balance force, net force equals 0, A equals 0. This guy, net force is going to be 15 up. So net force equals 15 newtons up. That means acceleration is up. And elevator problems. I freaking love elevator problems. You're going to love them too, I promise. So your mass is 75 kilograms, and you're standing on a bathroom scale in an elevator, because that's what we do in physics. We take bathroom scales on elevators to test this crap out. So starting from rest, the elevator accelerates upwards at 2 meters per second squared for 2 seconds, and then it continues at a constant speed. Is the scale reading during the acceleration greater than, equal to, or less than the scale reading when the elevator is at rest? All right, so to do this, you want to draw a free body diagram. So here you are, or here's the elevator. Here you are in the elevator. Here's the scale you're standing on. And it says that we're accelerating upwards at 2 meters per second squared. So that equals your acceleration. You have a mass of 75 kilograms. It's obviously a dude because he's about 150 pounds. And it wants to know, let's go back and read it again. Okay. It wants to know the scale reading during the acceleration, so during this 2 seconds, is greater than, equal to, or less than a scale reading when the elevator is at rest. So what does the force read when it's at rest? What does the scale read? The scales read forces. It actually reads a normal force. So the scale at rest. So at rest, what does the scale read? And we know that the force equals mass times acceleration. So it's your mass, 75 kgs, times your acceleration, which is 9.8 meters per second squared. We're talking about force of gravity, which is weight. So weight equals force of gravity, which equals mass times acceleration. And our acceleration is gravity. So 75 times 9.8 will give us 75 times 9.8. You get your weight is 735 newtons. Now this is your weight when it's at rest. Do you think it's going to change after you start moving? You betcha. Alright, so now it's for the free body diagram. Free body diagrams don't draw anything but a box. I promise you it'll be so much easier if you don't try to draw, airplanes and people standing on scales. It's a lot less confusing if you just draw a box with some arrows. So what are the forces acting on this person as the elevator is moving? So all this is at rest up top. And now down here, elevators moving on up. So you're going to have your weight. Your weight. Weight equals mass times gravity. You're going to have your normal force. We know we're accelerating upwards at 2.00 meters per second squared. All right. Now this is how you solve Newton's laws problems. Net force equals mass times acceleration. We're talking about acceleration in the y direction here. All right, net force equals the sum of all forces. What forces do we got going on here? We have the normal force going up, and we have the weight going down. So that means we have to subtract the weight from the normal force. Okay. So now this is how you start the problem. Now we know what acceleration in the y is. We know what w is. We don't know what the normal force is. That's what we're trying to find. Because scales, when you stand on a scale, it doesn't actually read your weight. It reads the normal force. And I'll show you why. That's why we like elevators. All right, so we solve this guy for f of n. So we add w to both sides. So we get normal force equals mass times acceleration in the y direction plus w. So we added w to both sides, got rid of it over here, and so on and so on. Now normal force now equals mass times acceleration in the y. And w equals mass times gravity. Mass times gravity. Both of these guys have an m. We could pull that m out. M times ay plus g. And I'm running out of room, so I'm going to come up here a little bit. Now we can plug in our numbers. We know our mass is 75 kilograms. We know acceleration in the y is 2. We know our gravity is 9.8 meters per second squared. So we know our normal force is going to equal 75 kilograms times 11.8 meters per second squared. So we're going to get, sorry, this is getting a little confusing. They're just getting messy. So our normal force, 75 times 11.8. You get a normal force of 885 newtons. Pretty cool, huh? You're traveling in that elevator and it's accelerating upwards. I'm sure you've all felt this feeling. It kind of feels like you're pushed down on the ground a little harder. If you had a scale underneath you, it would actually show that you'd weigh more while the elevator is accelerating up. Now what happens when that elevator, after that 2 seconds, after it's traveling at a constant velocity? At a constant velocity, that means your acceleration over here now is going to be 0. So you're going to have the same weight as you would at rest, because we're not adding that acceleration. What about if your acceleration was negative? Huh? Let's erase some of this stuff. Let's leave that. Get rid of this. So let's say we're starting at the top floor. Oh, I could have left that. I'll put it back. So let's say we're starting at the top floor and the elevator starts to move downwards. You get that kind of feeling like you're like a little lighter. You feel like the blood like rushing to your head and stuff. It's the same equation, except for this time, let's say it's going down at 2 meters per second squared. So we do 75 kilograms times -2, because the acceleration is downwards now, plus 9.8. So we get 75 kilograms times 7.8 meters per second squared. And we calculate that. Oops, syntax error. Hate those. Damn syntax. All right, now you get a normal force of 585 newtons, which makes sense. It should read less than what it does at rest, because you've all been in elevators before, and if you could actually feel yourself getting a little lighter. Now, what happens if that, let's say the cable snaps, you start to fall. Oh no, everybody's falling. How fast do you in that elevator now fall? So if you're falling, the elevator is falling, you all have the same acceleration. That acceleration is going to be the acceleration due to gravity. Everybody's falling at 9.8 meters per second squared. Using that same formula down here, the scale is going to read mass times acceleration plus gravity. So your normal force is going to be 75, why do I keep putting 0.75, times -9.8 plus 9.8. So now your normal force is going to be 0, because this guy in here is 0. Now what does that mean? It means you're experiencing weightlessness. Astronauts in space, this is why they can float around, because they're actually falling at the same speed as the space station around them. But you're also orbiting, and we'll talk about that when we get to orbital mechanics. But everything's falling at the same rate, so you just appear weightless. It's apparent weightlessness. Pretty nifty, and that's all I have for you today. Thank you.